What's up, guys? This is Matthew Burns, and welcome to your 5th tutorial on how to build an 8-bit computer entirely out of individual logic gates. In the last tutorial, we talked about 2's complement and how to perform subtraction using this method. In this tutorial, we were going to construct this setup that I explained in the last video, but I was getting a little bit impatient and I really wanted to see if it worked before I began rolling the camera, so I actually went ahead and built this already, but I will go through everything I did step by step. As you can see, the setup looks kind of similar to before. I have a third breadboard here with 2 chips. They're 74HC86N exclusive OR gates, and then one 74HC08N AND gate. Actually, excuse me, this one here is the exclusive OR gate, as is this. The chip in the middle is the AND gate. I still have the LED matrix hooked up, and all the sums of the full adders are hooked up to the LED matrix in the exact same manner as they were before. The only difference is I have all the B input connections going to all the B input connections are going through these exclusive OR gates, and all the pins, so one input of each exclusive OR gate is connected to one input from the B bus, and the other input of each exclusive OR gate is connected to this here, let me see if I can zoom in. There's one point on the breadboard where I have the second input to the AND gate and the second input to all the exclusive OR gates hooked up, all at one point, and I have one 10K resistor drawing them all to ground, and then I have a button. You can't see it through all those wires. There we go. I have a button that will pull them all high when I push that button, and what that'll do is when I pull the control pin of the exclusive OR gates high, all of those inputs from here, the B bus, will be inverted, and because when I push that button I'm also supplying a 1 to the control pin on the AND gate, the other pin is held high, the AND gate will supply 1 to the initial carry-in, the carry-in on the first adder, so that will invert all the bits and add 1. I needed 2 74HC86N chips for this to work, obviously, because I needed 8 exclusive OR gates. I only needed 1 AND gate, and I know it's kind of a waste of 3 AND gates, but I had to use an entire chip. I couldn't physically split a chip in half. But as you can see, I have the power and ground connections going to this third breadboard that I never had before. It's the exact same. 14 is power, 7 is ground for those chips, and other than that, nothing has really changed at all, other than the button in that setup. So when I push the button, it performs subtraction. When I leave the button unpushed, or don't send a signal to all those exclusive OR gates and AND gate, it performs addition. So right now, I have loaded onto the A bus, I have 16. I don't know if you can see that. I'll try to zoom in. I have 16. And then on the B bus, I have, what is that? 1, 2, 3, 4, 5, 6, 7 loaded onto the B bus. So 7 plus 16 equals 23. So if I were to hook up the battery, it should be adding as of right now, and you should see 23 on the LED matrix. Which you do. That pin, I guess it's farthest to the bottom of the screen, but really it's farthest to the left, is 16, and the other is 4, 2, and 1, 16, and 7, that's 23. And now if I were to push the button for subtraction, here, holding this camera is kind of difficult. Let's see if I can get a better angle, maybe if I tilt the camera up and zoom in. Now if I were to, that's not going to work. Push the button, it'll subtract 7 from 16, which equals 9. So you should see 8 and 1 be lit up, which you do. So this this setup that we built to perform the 2's complement with our arithmetic logic unit does in fact work, and I tried to explain this as clearly as I can, but let me just run through one last time what this is actually doing here. All the A inputs, all the bus for the A inputs, all 8 of them, we left alone. They're going straight to the different full adders. The B input here, I have the input, every single one of these B inputs is actually going to an exclusive OR gate, and the other input of each exclusive OR gate is going to a control button. And when I push that control button, it pulls them high. And when the second control pin of the exclusive OR gate is pulled high, the binary data that we're getting from the B input is inverted on the output of the exclusive OR gates. In addition to that, I have one AND gate here on this chip. I have one of its inputs pulled high, and I have the other input going to the control pin. So when I push the button to draw, when I push the control button high, it will send a signal to the control pin on the AND gate. The output of the AND gate will go high, and that will add 1 to the initial carry-in, or the carry-in of the first full adder, and that will effectively invert all the bits and add 1, performing the 2's complement. So I hope you enjoyed this tutorial, and in the next few tutorials I will actually be covering something I was thinking a lot about: how to perform multiplication on this. And I'll explain this in the next tutorial, but there are 2 methods I'm still deciding on. They're both essentially the same, but then when it comes to adding all the results, I can either add them one at a time through one full adder, this thing that we constructed here, or construct 7 full adders and add them all at once, and that will speed up the computer immensely when performing this function, but it will also be much more costly on parts. So I'm still deciding that, but I'll let you know when we get to the next tutorial. Again, thanks for watching, and I hope you enjoyed this video.